have a sample problem. It says 2 points I and F in a uniform electric field. So the points lie on the same electric field line and are separated by a distance d. So find this potential difference VF minus VI by moving a positive test charge Q0 from I to F along the path shown, so which is parallel to the field direction. Okay, so in this problem, we will imagine there will be two paths. One is this one, and we'll have another one in part B. So with the same initial and final points. So and then we will just verify that the potential difference doesn't really related to the path itself. It's only related to the initial and final points. Okay, so here we try to calculate VF minus VI as requested by the question. So VF minus VI equals negative integration of E dot ds from I to F. Yeah, from I to F. Okay, so here E field is pointing downward, and then the path is from I to F, which means that ds is all the way pointing downward. So E and ds points to the same direction, which means E dot ds is nothing but E times ds. And actually, this is a uniform E field, so it is nothing but negative E times d. D is the distance from the initial point to the final point. Okay, so we have a negative ED, which is the question to part A. Okay, so yeah, so next we consider part B. So now we find the potential difference VF minus VI by moving the positive test charge from I to F along the path ICF. So this is I, this is C, this is F. So this is field D, which means that if we just consider these 2 points, it is actually the same as the one we've done in part A. But here we go for another path from here to here, and then back to point F. B minus BI equals negative integration of E dot ds from I to C. Okay, so here ds point to the right side, E field still pointing downward, which means that E dot ds is 0 because these two vectors are perpendicular to each other. Okay, so the inner product will be 0. So we have a 0 for the first part. And then we would like to also calculate VF minus VC. Okay, so which will be negative integration of E dot ds from C to F. From C to F. Okay, so it is this way. So from C to F. So and then for this path, this is also D. Okay, so this is actually a right angle triangle. This is 90 degree. This is 45, 45. Yeah. So you can see this is ds, and E has an angle of 45 degree, which means that E dot ds here, E dot ds will be E times ds cosine of 45 degree, or you can say pi over 4. So cosine of pi over 4 is square root of 2 over 2, or 1 over square root of 2, like this. Okay, so we have something like a negative integration of c f, and then we have an e ds cosine pi over 4. So this one, for this one, it is nothing but e times the distance. So this is right angle triangle. This is d. This is d. This is d. This is d. So this length will be square root of 2d. So this is nothing but negative e times square root of d, square root of 2 times d, and then times this is square root of 2 over 2. Oh, yeah. So this is nothing but negative ed. Okay, so we try to add these two equations together from here, and then also here and here. So we just add them together. So VC and negative VC will cancel. So when we try to add them together, we have VF minus VI equals 0 plus negative ED will be negative ED. So we just, we actually didn't prove, but we try to verify that if we just move a charge from I to F along different path, this path is directly go from I to F in a straight line, and then here we go from I to C and then to F, then the potential difference are actually the same. Okay. So next we consider the potential due to a charged particle. So here we also use the same formula, which is delta V equals negative of this line integral of E field. So here, here we assume that this is the charge which will generate the E field and also generate the potential in the space. And then we try to place a test charge, a positive test charge here. And then of course the E field will try to push this, because both of them are positive charge, they will attract, they will repel each other, so that it will change the potential of this test charge. Okay, so suppose initially the test charge is at capital R. This is capital R. This is the initial point. This is the initial point. And yeah, so this is the initial point. And then for the final point, it is at R tends to infinity, infinitely far away. So this is the, sorry, what is that? Wait, wait, what? Okay, so yeah, so let's move back. Yeah, so here, yeah, so yeah, so this is the initial point. We try to move the charge to infinitely far away. So here we have Vi. We assume this point with a potential V, and then infinitely far away, Vi equals V, and then for infinitely far away, we assume Vf equals 0. So if at infinitely far away, the potential is 0 at the infinity and here. So we try to put this one into here. So we have 0 minus V. And on the right side, as the initial point is as R. So we have R here, and then for F, for the final point, it is an infinite far away. So we have an upper limit of infinity. So the right side becomes this one, and then we try to plug in the, this one is the Coulomb's law. Is the Coulomb's law, E equals 1 over 4 pi epsilon naught times Q over R squared. Plug into here, and then we can do the integration because this is a function of R. All the other values are constant. Okay, so we plug this one here. We will get Q over 4 pi epsilon naught are constant, so we put them out, and then we have 1 over R squared. So we have dr over R squared here, integrating from capital R to infinity. So this is a R to the -2 power, and then here we will have 1 over R, and then the negative side cancel with this one, so this becomes a positive value. And then finally, we need to evaluate this 1 over R from capital R to infinity. So this one becomes 1 over infinity minus 1 over capital R, which is -1 over capital R. So we have a negative sign here. So this negative sign and this negative sign cancel. So finally, we have V equals 1 over 4 pi epsilon naught here, and then Q over R. Yeah, actually, this dumping variable here is capital R, but generally we will just replace capital R by small r, so the expression look like this. Okay. Yeah, so this is the expression for the potential generated by a charged particle. Okay, so here, if we have a group of charged particles, then we try to find the potential generated by a charge one by one, and then we try to add them together. But the fortunate thing is that the potential is a scalar rather than a vector. Then we don't need to decompose the vectors into different component and add the components correspondingly. So here the potential is an algebraic sum of the individual potentials with no consideration of directions. So this is the good point for introducing this potential. Okay, so here the highlight. So a positive charge particles produces a positive electric potential. A negatively charged particle produces a negative electric potential. So yeah, so it's just simple things, because V equals 1 over 4 pi epsilon naught, and then times Q over R. So actually, these are all positive. So if Q is positive, V is positive. If Q is negative, V is also negative. So nothing special. Okay, so checkpoint 3. So the figure here shows 3 arrangement of 2 photons. So rank the arrangement according to the net electric potential produced at point P by the protons greatest first. So yeah, so which is bigger? So you can answer in the chat room. So if you correct, then I'll mark it down for the for their attendance rate. So at ABC, which is greater, ABC. So actually, we would try to determine the net electric potential. Net electric potential. So which one is greater? Can anyone answer this? Highlight the checkpoint. Actually, we didn't really need any calculation. So ABC, which is larger, which is greater. Someone answer B, someone answer A. Any other question? Any other answer? Any other opinion? So you still have chance to get the right answer. So no one's answered correctly yet. A larger than B larger than C. Not correct. Okay, so I think no one can get it. So let me try to tell you the correct answer. The correct answer is they are all equal the same. Yeah, so they actually they have the same potential. They have the same potential. Because here we don't really need to care about the we don't really need to care about the direction. So in this case, so all of these red dots are protons, so which means that the charge amount are all the same as an elementary charge E. So for ABC at point P, the potential will be nothing but 1/4 pi epsilon naught times E over D plus 1/4 pi epsilon naught times E over capital D. So we have two charge for each of the case. So we need to calculate each one by one. So this one corresponding to this one, and then this one correspond to this one for part A, and then this one correspond to this one, and then this one correspond to this one, and similar for this one. We don't care about the direction because they are scalar. They are scalars. So we just add them together. So they have no way to cancel in this case. But if you consider the E field, if it is E field, then I will say E field at point P for the part A will be larger than the one in part B will be larger than the one in part C. Okay, so that's for E field. For E field, I would say A is larger than B is larger than C. But when we consider the net electric potential, they are actually the same. Okay, so let's take a look at this sample problem. Okay, so it says, what is the electric potential at P located at the center of a square of point charges? So the distance D is 1.3 meter, and the charges are Q1, Q2, Q3, Q4. So nothing special. Yeah, if we need to calculate the E field at point P, then it will be, yeah, need more calculation. But yeah, in this case, it is not that difficult. So this is a square, and this is actually the center point of this square. So according to the Pythagorean theorem, we can quickly find the distance from point P to Q1, Q2, Q3, Q4 are all d over square root of 2, d over square root of 2, d over square root of 2 all the way. So in this case, we can just come up with R to be d over square root of 2. And the total potential at point P will be nothing but summation of dk, k equals 1 to 4, which is 1 over 4 pi epsilon naught times, let me see here. Okay, so I think here we still need to multiply by k because yeah, this is the expression, or you can write it as a k times q over r, k times q over r, like this. So here the k is missing for equation 2427. Okay, so here we have a summation of q1 to qk over rk, and then k is from 1 to 4. So you can write it as 1 over 4 pi epsilon naught times q1 over r1 plus q2 over r2 plus q3 over r3 plus q4 over r4. But in this question, r1 equals to r2 equals to r3 equals to r4 equals to d over square root of 2. So we have square root of 2 over 4 pi epsilon naught d, and then we have q1 plus q2 plus q3 plus q4. Okay, so plug in the values. We have a 1 over 4 pi epsilon naught is 8.99 times 10 to the 9th power, and then times square root of 2 over d is 1.3 meter, and then times, this is 12 minus 24 plus 31 plus 17 times 10 to the negative 9th power. Okay, so use a calculator. You can calculate that V is nothing but 350 volt. 50 volt. Okay, so actually the figure of the question, it tells you that this is the equipotential surface. Okay, so actually you cannot quickly find that the equipotential surface look like this, but simply speaking, we know Q1 is positive, Q3 is positive, Q4 is positive. So this equal potential surface will just separate the charges into two groups, which means that this is a positive charge, and a positive charge, and this is a negative charge. And actually, if you really need to find the equipotential surface at 350 volt like this, probably you need a computer software or simulation program to calculate all the equipotential, all the potential in the whole space, and then you try to find which value is close to 350, and then you try to connect them together to find this equipotential surface. But just simply speaking, you can see that we have positive charge inside and then negative charge outside. So yeah. And then here is another sample problem. So it says 12 electrons are equally spaced and fixed around a circle of radius r relative to v equals 0 at infinity. So what are the electric potential and electric field at the center C of the circle due to these electrons. So this one is easy. So V will be 1 over 4 pi epsilon naught. And then all the charge are negative E, so on and so forth. So we have 12 charge. So for everyone at point C, we just need to plug in a negative E over capital R. So we have negative E over capital R, but we altogether have 12 electrons there. So we just add 12 terms together. So it multiplied by 12 here. Okay, because all of them are E. And then all the distance are the same because it's a circle. It's center of a circle, and then all of the charge are negative E. So we altogether have this electric potential at point C. And for E field, does it ask? I think it, oh, yeah, it actually asks the electric potential and also the E field. So for the E field, we can quickly see that, for example, for this one and this one, both of them are negative E. So for the top one, it will generate the E field pointing to the top side, and for this one, it will generate the E field pointing downward. And the magnitude will be the same, but in opposite direction, so that they will cancel each other. So all the 12 electrons can be separated into 6 pairs. Each of them generates 0 E field. So the E field generated by these 12 electrons at point C will be 0. Okay, so here, if the electrons are moved along the circle until they are non-uniformly spaced over a 120-degree arc, what then is the potential at C? So the potential doesn't change at all because the charge amount doesn't change, and also the distance from here to the center, from the arc to the center, still the same. So when we try to calculate the electric potential, it will actually be the same value. However, in this case, if we try to calculate the E field at point C, here if the E field is not 0 anymore. Of course, we don't know the position of each of the electrons, so we have no way to calculate the E field generated at point C. The only thing we can tell is that the E field at point C for the part B is not 0 anymore. Okay, so let's move to the another part. So here, it introduced the potential due to a electric dipole. So just now we already know what is the potential generated by a charge. So which is nothing but 1 over 4 pi epsilon naught times Q over R. So yeah. So here we have two charges, so we just need to add the potential of the two charges together to know the potential generated by the electric dipole. Because in chapter 22, we already know the definition of an electric dipole is two charges with the same magnitude but opposite sign placed close together. Then it will be a dipole. And the dipole moment is Q times D, as shown here. This is the dipole. It is the dipole moment. Q times D will be the P vector. Okay, so here, rather than because V is a scalar, so here it is possible to find the potential out of Z axis, because in chapter 22, when we try to calculate the E field generated by the dipole, we can only calculate the E field along the Z axis, and also we will assume the distance we concern is far away from the dipole. So this z is much larger than d, something like that. With this assumption, then we can calculate the E field generated the dipole along z-axis. But here, v is a scalar. It is easier to calculate, so we can come up with the solution. The potential generated by the dipole out of z-axis, and it is actually related to the angle between z-axis and PO. Yeah, so this is the angle. Okay, so here it says V equals V plus V minus, so nothing special, and which is 1 over 4 pi epsilon naught, and then times Q is the positive charge over R plus. R plus is the distance from the positive charge to the point P we concern. And then here the negative charge, of course, negative Q here, and R minus is from this negative charge to the point P we concern. Yeah, so this is nothing special. And then we can try to multiply as a common denominator, R plus R minus. So we have Q is the common factor, so we can put it out. We have R minus minus R plus in the numerator. So we need to come up with this one. Okay, so you can approximate the two lines P as being parallel and the length difference as being the leg of the right triangle with the hypotenuse D. Okay, so here we also assume that this point P is far away from the dipole, just so we can, so here we assume that this point is infinitely far away. So we can assume that when we try to connect P with this positive charge and P with this negative charge, these two lines are parallel. If this P is not far away enough, then of course you can see, oh, this is not so parallel. But here, if we assume that P is far away enough, then and then P is far away enough, then we can assume this line is parallel to each other. Then we can have some approximation. Okay, so suppose P is here. Suppose P is here, P is here. So this is R plus, this is R minus. So this part and this part, we can assume it to be the same length. So the difference, because we need to come up with R minus minus R plus. And so this part will be R minus minus R plus, this one. And yeah, so here we have R minus minus R plus should be D times cosine of theta. Cosine of theta is this side divided by this side. Okay, so R minus minus R plus is approximately D times cosine of theta. And for the denominator, R plus R minus can be approximated as R squared. So we just, for this part, we just approximate R plus is approximately R, R minus is approximately R. But we cannot apply these two for here, because otherwise this is approximately 0, but it means nothing. So we cannot apply this approximation for here. We can only approximate for the denominator. Okay, so here we can approximate V to be this expression by plugging in this one to here and then R squared to here. So we have Q over 4 pi epsilon naught and then D cosine of theta over R squared. So using the definition of the dipole moment. So we exchange this one to be P. So we have, this is K times P cosine theta over R squared. So this is, so if you have chance to study the electromagnetism, if you are an ECE student, so this is a so-called antenna model, 天线的模型 antenna. So this is so-called a monopole or dipole antenna. So for the dipole antenna, it means that it is related to the angle. It relates to the angle between the point and this axis. So if theta is 0 degree, then cosine of 0 degree is 1. So it maximizes the electric potential. However, if theta is pi over 2, 90 degree, then cosine of 90 degree will be 0. Then yeah, so in that direction there will be no electric field. There will be no electric field. So just like your mobile phone, you should have multiple of antennas for different bandwidth, like Wi-Fi or 3G, 4G, or even 5G should have a different antennas. So you try to change the current going through the antenna, then the antenna will generate some so-called EM wave in some specific direction. Some of the direction, the EM wave will be weaker. So this is a simplified model for an antenna. Yeah. Okay, so the next point we introduce is the potential due to a continuous charge distribution. So it is similar as what we have done in chapter 22, but here the potential is a scalar. So yeah, so it makes the calculation easier. So we take similar steps. So for continuous distribution of charge over an extended object, the potential is found by dividing the distribution into charge elements dq that can be treated as a particle, treated as particles, and then summing the potential due to each element by integrating over through distribution. So yeah, so we just save the cancellation steps. So because it is not a vector, so we don't need to decompose the vector into different components and then cancel some of the components. Okay, so we now examine two continuous charge distribution, a line and this. So we do the same structure as before, but here we would like to calculate for potential rather than the E field. So here we assume we have a line L here with line of charge, and of course lambda is the linear charge density. Lambda is the linear charge density. Okay, so here we try to find the potential at point P. Okay, so here we try to separate this line into many small segments. So separate it. So within it we have dq. We have dq for every small segment. And then, for example, for this one, we have dq. So we have dq equals lambda dx. So lambda is the linear charge density. So it multiplies by dx will be the charge at that part. Okay, so then we try to calculate what is the potential generated by that part. So which is something like this. So dv equals 1 over 4 pi epsilon naught times dq over r. So here dq equals lambda dx using this expression. Dq equals lambda dx. So just plug in this one into here. And then r, for r, from this point to here. So this is r, and according to Pythagorean theorem, r is square root of d squared plus x squared. So we have here r equals square root of x squared plus d squared. Okay. Or maybe I can draw the arrow here. Okay, like this. Okay, so here we need to do this integration because lambda is a constant. These are constants. So we need to do this integration. And then, so the total V generated by the whole bar will be like plugging in this one into here. So we have a lambda over 4 pi epsilon naught here. And then we have a dx over square root of x squared plus d squared here. So this term is x squared plus d squared to the negative 1/2 power dx. So yeah, so learning the calculus, suppose you have learned the calculus, so you should know how to come up with this expression. Okay, so if you don't, so let's do it quickly. Here we just assume x to be d times tangent of theta. So if theta is zero, then x will be 0. So when theta to be 0, it corresponds to x to be 0. And also when theta equals L, theta, it should be like x to be 0, it corresponds to theta to be 0. And then if x is capital L, it corresponds to theta to be something else. So let's see. Suppose we have this expression, and this is theta. So this is x, this is d. So x over d should be tangent of theta. And then this is d squared plus x squared, and then take the square root. So here, if x is if x is x, if x is capital L, then theta should be arctangent of L over d. Just plug in x to be L here. Then theta should correspond to arctangent of L over d. So, and also dx should be d secant square theta d theta. Okay, so then we can just plug in the original expression. This one is, so integration of x squared plus d squared, and then to the negative 1/2 power dx from 0 to L would be x to be d tangent theta. So this one will become d secant theta in the denominator, because we need to take the negative 1/2 power. So it goes to here, and then dx equals d secant square theta d theta. And then this is from, maybe we can call it theta L. So this is from 0 to theta L, which is arctangent of capital L over D. So we can do some cancellation. D and D, secant square with secant. So here we have a trick to do this integration. So secant of theta and then d theta, we can multiply secant theta plus tangent theta and then divide by secant theta plus tangent theta. So it changed nothing. And then here, this one will become d secant theta plus tangent theta, or just swap it away, swap these two terms. So d tangent theta will be secant square, and then d secant square will be secant tangent. Okay, so yeah, so it's just like a change of variable, but without explicitly doing it. So so it becomes natural log of secant theta plus tangent theta from 0 to theta L. Okay, so here let's do this. So we need to know what is secant theta. So secant theta will be secant theta L will be d squared plus L squared square root over d, and then tangent theta L would be L over d. So you can just plug in this one and this one to here. So we have lateral log of square root of a d squared plus L squared, and then plus L all over D, like this. So it is actually this one. Okay, so maybe we just stop here today.